Okay, so um, today we're gonna go into hydropower. So that's your chapter 3 in your textbook. So hydroelectric dams, okay? Dams are nothing but they're just the structure, and we're gonna call these like barriers, yeah. So what are we doing? We construct, all right, these dams or barriers to hold back the water, okay? Um, Usually we raise the level, right? So if you go to any dam uh, in your town, you're gonna see definitely we raise the level, all right, of that dam, and and to hold the water, okay, so keep the level up, make the reservoir, and then we can use, all right, that water to generate electricity. So the level is elevated because we want that water flow, okay, by using the gravity. So the force is going that way, yeah. Put the water up, barricade it, okay, contain it right in the dam, and then we're gonna let that flow by using gravity. And then when the water flow, all right, water mass is really large, yeah, big, okay, masses. So when they move, they bring the energy, okay, the mechanical energy coming out from your kinetic energy movement, okay, so movement. So Ke is going to convert it into Me, which is your mechanical energy, and we're going to use that, okay, to run the generator and then produce electricity, okay. So you have to get, all right, these connections, all right, of these processes, and also your energy conversion, okay. So many of the dams in the United States, they constructed in the early 1900s, okay. They are very large, okay. They are definitely man-made structure, okay. So in 1930, we're generating about 40%, okay, of the electricity by using the hydroelectric dams, okay. So that's 40%. So that's pretty huge. You know, in 2015, okay, we produce about 45%, okay. And in 2015, the wording changed, all right? The term changed into renewable electricity, okay? Why? Because we are using the natural, right, power source, which is your water. And that's about like 6.1%, right, of your total US electricity. So where do you get the water? You get the water from river, right, and a stream, yeah? Okay, so other countries, so we have Norway, we have Nepal, and we have New Zealand and Canada. All right, they're using about 50%, yeah, for generating electricity using this hydropower. Okay, here's a chart. So we have two lines. So one is a blue and the other one is red. Okay, the blue is up and the red is down. And we have some percentages right here and then our years. Yeah, so we can be able to understand what this chart is talking about. It's just showing you, okay, this is our US electricity, and then you can see, right, as the year goes up, okay, you can see the increase, okay, in the hydropower, right, generated electricity, okay. And you may feel a little bit weird to connect these two lines, okay, but don't worry about it. It's just showing you that it's going up. So you're gonna stick to this year and ignore this, okay. And this is just you might feel like it's going down or something like that because of this slope showing you, but this is just showing you the US electricity, okay. And so the trend itself has it has its own value on the line, okay. And don't go ahead and relate it to the other line, okay. The other line is showing you as the years go, it is going up, okay, by using the hydroelectric dams. Hydropower, okay, we view it as renewable energy because they are environmentally very friendly, yeah, of other types of electric city power sources like nuclear, okay, and fuel burning, right, electricity generators. So that's pretty clean energy. The downside is like you definitely need capital, capital because it comes with a very large construction. So everything that you have to build, you need lots of money, yeah. So that's the reason why it takes a long time, right, for completion. And but once already completed, you're expecting very low, okay, operating costs because you've got the system, and the system, we expect that system to be running, okay, for a long time. So as it runs, it generates a profit, and that profit is going to levelize all of your investment, okay. Plus, so once your investment is like pay off, then everything you've got, as long as that system is going to stay, is your profit, okay. So it's not so bad, yeah. Okay, so this is just a chart, and this chart is showing you this is average, okay, your power production expense per kilowatt hour, okay, just the expense is showing you. So the cost, all right, of generating electricity, okay, from various sources, you can see right here. So we have fossil fuel, steam, and we have nuclear, and we have hydroelectric, and then we have our gas turbines, yeah. And then we're gonna break that down, right, that cost, into three categories. And one is your fuel cost, other one's your maintenance or your system cost, and then your operation, okay, of your system. So operation, maintenance, and fuel. So that's the three things that you have to deal with for power production cost. So when you take a look at it, you see this is in terms of cents, yeah, not even dollar. So 100 cents is a dollar, yeah. So if you go by cents, that means like, okay, this Wisconsin Valley Improvement Company is going with your electric bill, right? So electric bill also go with the cents per kilowatt hour to calculate the electricity usage at your resident. So here we have three categories, and when you take a look at it, look at that. Your gas turbine, right, cost is highest, okay? That's because when you pay attention to the category, the fuel is very, okay, expensive. So if you try to think about the gas turbine in previous chapter, you understand we are using mainly what? Natural gas, right? And that, okay, natural gas is expensive, yeah? So here, when you take a look at this hydroelectric, right? So hydroelectric dams, you see, look at that fuel, yeah? Expenses completely zero. Yeah, see this? There's no green in here. So that means that we're getting fuel free, yeah, which is your water. We got the raw water from where? From the environment, yeah, from the rivers and the stream. So therefore it's completely zero out right there. Of course, you have to maintain, and the other one, operation, is pretty big, yeah. Is the second biggest cost compared to other categories. So here, nuclear, the same thing. The fuel is not, okay, as expensive as in natural gas or for gas turbine. And then we have fossil fuel. Okay, this is expensive because fossil fuel is your petroleum, right? You got to dig it out, right, and then process it in order for us to be able to use it. So therefore, the fuel expenses, you can see, okay, second to the gas turbine. And then they have their maintenance and then operation. Okay, nuclear operation is the highest, yeah, because it's very dangerous, okay, very risky to the labor, okay, serving at the nuclear plant. Also, they can also have all forms of cancer, okay, that goes into genetics, meaning like your next generation might get affected, yeah. So it's not so good, but we will try all our best, right, to get rid of this as soon as possible in the future, and to increase this. But those are just a plan, we don't know how long it's going to take, right? And the second one to get rid of is this one, and that's because we're not trying to get rid of it. It's that the nature itself is trying to get rid of it, because the regeneration of the fossil fuel, okay, is it takes like millions and millions of years, and we don't have enough for the entire world, okay? So that's working on, and this got to go up right now. So we don't have a lot of choices, right? Oh my gosh. All right, so let's go to the next one. Okay, this is just a cross section, okay, of your pumped storage plant. So we store the water right here in the reservoir, yeah. So every time we want to generate, okay, the power, we're gonna let this water coming into this, all right, root, and then I'm gonna here we call that's a power plant chamber where you are generating, okay, the electricity. Okay, the turbines are right in there, the generators are right in there, and okay, take this kinetic energy, which is a water motion, and change that into mechanical energy in the turbine blades. Okay, and then turbines are used to run the generator and then turn that into electricity. Okay, so that's pretty much the processes. Yeah. So here, the whole thing, your surge chamber, the power plant chamber, and the breakers right there. So these are all the controls. Yeah, and transformer volt is for the voltage, because you have to play with the voltage that okay accompany the current, which is your electricity. Okay, and then the water is going to go into the discharge, which is your river. Yeah. Okay, so this one is a Hoover Dam, right? So that's in Colorado River, and you can see the river right here, and we're gonna pump that water up and store right here. Okay, so this is your reservoir, and that's your dam, and people can go right from here and then take pictures or something like that. Anyway, so when you draw the cross section, all right, blueprint, remember the previous slide diagram, that's what you see, okay, inside where all the pumps are. Yeah, so we divert this water into here by, and you can see the elevated, okay, the level right here, okay, and the level right here, so that's we call the elevated level. And because we want to, okay, get the energy, so the energy is manipulated by using height. Okay, so every time you raise the height, we are raising the force, okay, of your gravity. Okay, your gravity is g, yeah, acceleration, so it can bring with that much of acceleration and speed down from that height all the way to the ground. Okay, so that's what we're doing. And don't forget your physics, yeah. So your potential energy. So let me write that down for you here, your PE, okay. So dam is, we are creating a PE for a short period, okay, before we running the kinetic energy back. So PE is, okay, I'm going to write it, it depends on your height, okay. So you have your mass, so that's your mass of your interest right now, water mass, and then height is the height, okay, from the surface of the ground, okay. So m, and then you also have, I'm gonna write it down here, g, okay, g. So mass, gravity, and then your height. Okay, we have a mass, water mass, we have a gravity, okay, acceleration, okay, pointing directly to the core of your earth, okay, and then you have a height, which is a height above the surface of your ground. Okay, so this is how we store the potential energy. So now this water mass has a potential energy this much. Okay, so you multiply the weight of the mass. We know the weight of the mass because we know the exact specification of the size of the dam. Okay, so we know the area, you know the volume, so therefore we can be able to get the mass of that. You can weight it. Okay, and we know the gravity, that's a 10, okay, meter per second square, and then you know the height because from the construction you have a precise height, okay, for this dam, and you calculate it by multiplying all of that values, and you can be able to get that tremendous potential energy contained right here in the reservoir. When you release it, we're gonna use, okay, that energy and then convert it into kinetic energy, okay, meaning like the water is now running. So use that motion, kinetic energy, and then turn that into mechanical energy, okay, running the turbine, okay, running some sort of a generator, okay, to produce electricity. Okay, you got it. Okay, so instead of air, we're now using water. Okay, for air, all we have to do is suck it in into the compression chamber. For water, we have to pump it up into the dam. Okay. Okay, so Hoover Dam, you know how it functions. So this is a famous dam in the United States, most famous, right? So they have like a 17 generators, yeah, and we produce about 4 billion kilowatts hour, okay, for electricity every year. And we also use it for flood control, okay, and also navigating the water, okay, from the flood into here. Another largest reservoir in the country, okay, is your Lake Mead Reservoir. So Lake Mead is also in Colorado, okay, in the state of Colorado. So original copper cable, right? It was designed and it can carry about 287, right, 1,500 volts. Okay, that's pretty big number. And that is going to carry the electricity from the dam, right, generator. So we got 17 generators right there at Hoover Dam, right? And we're going to carry the electricity by using metal cable, okay? So metal cable, they can be able to transfer, okay, that motion, which is your electron, okay, flow. So electron is nothing but a little, very, very small particle, right? And they move, yeah? So they can be able to move through that cable, okay? It's kind of like a domino, okay? Like it's not that electricity or electron is going this like this, okay? It's just like it is similar to domino effect, okay? Just colliding, okay? The electrons in front of them, and then the next, okay, electron in the sequence, okay, is gonna go and carry that, all right, bump. I will call it bump, and then keep going, okay? And you gotta review, okay, your atomic structure and how the electron can be aggressively activated, okay? So every time the electron is activated, it's going to come in and out of that, okay, atomic energy level, right? That's how the cables, okay, inside of the cable at the atomic level is going on in that way, okay? So this is how we generate the electricity and transport the electricity, okay, which is nothing but, I would call it just transporting the activated motion, okay. You can activate the motion by using some form of mass, okay, and structure, okay, and we're going to transfer that motion into smaller particles, okay, smaller particles, and then we're going to carry the moving, right, or activated particles inside of the cable, yeah. So you don't want to go and mess up with all the cable, you know, electric cable along the road because it's highly activated, okay, and you don't want to get shocked and die. So definitely don't go and mess up with that because the voltage right in there is, you can see this much, yeah, that can burn you alive right there at one shot, yeah. Okay, so anyway, that's a 287 miles away, okay, in Los Angeles from Colorado, okay. So why do we have to say this one is by reading this, you can understand how powerful, yeah, how powerful that motion is, how powerful that energy conversion is, okay. It can go 287 miles, yeah, that's a lot. But of course, this much of intensity coming out from this power. So once this electricity reach, okay, to your residential or commercial or industrial, all right, location, okay, here's your house, and you have something called transformer, okay, and you're going to bring the voltage down, okay? You always have an electric box, all right, next to your house, and this is where what we do is modify, okay, the speed of that flow in the electric cable, right? So this is a cable from your street, and then it's going to come to your box, and from your box to your house, okay? So going that way, okay? So what are we doing? We are controlling the speed. We're controlling the volts. When you control the volts, you're controlling the speed of that current, okay? Current is your I, which is the flow of your little particles, electrons, yeah? So make sure you try to connect with your physics. So Hoover Dam, we're going to go back to our construction and take a look at it. So they started in 1931, and it was turned over to the government, okay, in 1936. So they say that's like more than 2 years ahead of the schedule. So that's pretty good, yeah. So 726.4 feet high. Okay, we raised to that level from the ground. 1,244 feet long. So that's how long that dam is. 45 feet thick, okay, at the top, and 660 feet thick at the base. Okay. And we have about like 4.4 million yards of concrete used up in this construction. Okay, so that's a lot. You can calculate the cost by multiplying, okay, with your concrete price. And that's just a concrete. We have other stuff too. So you have to understand, how high, the expenses to construct something. Construct a huge system to generate electricity. Okay, so from this Hoover, alright, plant. So from this plant, what do we get? So we got about 56% power distribution in California, and Nevada is getting about 25%, and Arizona is getting about 19%. Okay. And oh, we don't see any Colorado in here. Okay, you might want to think about it why. Alright, so next example in hydropower, okay, is from South America. So this is outside of the United States, and you can see a picture right here. You can also Google it. Have more better picture. This is just to give you an example. And so this is like a Taipu, okay, hydroelectric power plant. Some people say like Itaipu. Some people go with a silent, okay, I. So it depends on however you want to pronounce it. We don't have to care about it anyway. Just make sure you get the spelling, okay. So it is on the built, okay, on the Taipu River. That's in South America, okay. So it is on the Brazilian and I think Paraguayan, okay, border, and that's not so far from your Argentina, okay, border. So they built it in 1975 and completed in 1991, okay. So capability about 12,600, okay, that's megawatts, okay, and the output about 75 million, okay, megawatts hour every year. So they've got like 18, generating units, and each one of them is doing about 700, okay, megawatts. So that amount in a single powerhouse is totally enough to power most of California, okay. So that's pretty powerful, hydroelectric power plant. So this Taipu, dam contributes about 75%. Okay, Paraguay's power needs, that's just a country name, and about 17% for Brazil. And we're going to take a closer look at construction, okay, material. So iron and steel, use it in this dam, right? So if you think about it, you can be able to build like 380 Eiffel Towers, okay, with that amount of material used in this dam. About 15 times, okay, the concrete used to build, the tunnel between the England and the France. So get that amount times 15, okay, and that is the amount of concrete we use, okay, right here in this type of hydroelectric power. So that's a giant, okay, gigantic, all right, um, dam, okay. Okay, so next example is your Three Gorges Dam. We'll take a look at this. So this is another hydroelectric dam, okay. So that's using the water from the Yangtze River, okay. So that is in China, okay. You don't have to know all of this, okay, stuff, difficult to pronounce. I believe there's a town of a San, okay, Sandupin, and then in a Yilan district in Yicheng, okay, Hubei province, so that's up north in China. So you can copy this and then Google it and see where that, okay, province is in China, and you can be able to know all of this. Three Gorges Dam is located right there. Alright, so that's the world's largest power station in terms of installed capacity, and that's about 22,500 megawatts. So that's equal to about 15 nuclear reactors. That's pretty powerful. So each main turbine, they have like about 32, okay, and they have capacity of 700, okay, megawatts. Of course, this is each. Then the dam is designed and intended to increase, okay, Yangtze River's shipping capacity. And also, of course, all the dams are used, okay, for flood downstream again, okay. Definitely provide the flood storage, okay, space, meaning like we're trapping the water coming out from flood in this reservoir, okay. So that way the water won't go, into the land and mess up other people's plantations and things like that. Yeah. So systematically rooted into the reservoir. So okay, about 37 billion, okay, dollars, of course, to build, because this is a very big structure, and they generate 11 times, right? Power, okay, as much as the Hoover Dam can generate. So meaning like Three Gorges Dam is bigger, okay, than Hoover Dam, therefore produce more, okay, electricity, that is 11 times than Hoover Dam can produce. Okay, now we're gonna move around the mass of water, and the dam literally slowed down the rotation, okay, of the Earth. So that just geographically, since you know that our planet, okay, our Earth is, where's my, okay, here we go, is round like this, okay, and it is definitely spinning on itself, and also, okay, my arrow is pretty bad, and also rotating, of course, in your solar system, okay, orbiting, which is orbiting around the sun. So what's this bullet point is saying is this dam is very huge, okay, it is very, very huge. It's the world's largest one, and it can store, okay, massive amount of water in there, to the point, okay, that it can slow down the rotation of the Earth, okay. So that much of power, it can be able to influence even to the Earth, okay. So how much speed? So that's a 0.66, okay, microseconds, okay, slow down. So that's a 42 billion tons of water right in there, in that reservoir. So how big the Earth is, and the speed, how huge that is. Even the 42 billion tons can only slow down 0.66, and not even seconds, microseconds, yeah. Okay, this is just showing you like two diagram in 1987 and 2006 for Three Gorges Dam right there. Okay, this is after construction, of course. So building this dam, alright, flooded archaeological and also the cultural sites. So you can see, look at that, okay, how different, okay, the terrain, okay, became after the construction. Yeah, very different. And also, okay, the construction of this dam displaced about 1.3 million people, and is causing significant, okay, ecological changes. So one big construction can influence this much. including, okay, the increase in the landslide, okay. So you can see all the lands are chopped out of here, all of this. And if you pay attention to the vegetations right there, see how all of these trees are gone, yeah? We chopped it up. Here in 1987, you still have trees, yeah? This is before the construction, of course. So 13 cities, 140 towns, and more than 1,600 villages, okay, have been submerged under the world's largest reservoir, okay? All right, and then we are going to get into the specifications. So the height is 181 meters, so that's 594 feet. Your length is, okay, 2,335 meters, so that's 7,661 feet. Your crest width is 40 meters, so that's 131 feet. Your base width is going to be 115, all right, meter, that's 377 feet. So this is a real life picture right there. It would be very difficult for you to be able to see it because you got to be on that side to be able to see the height and the base, okay? So you can just read it through and that's okay. And probably you will want to find a video, okay, of Three Gorges Dam on YouTube or on the internet, and you can be able to see these specification, okay, in these videos or picture as well. So the spillway capacity is 116,000, okay, meter cube per second. So that's about like 4,000, okay, 100 thousand, okay, cu feet per second. And cu is nothing but a cubic feet. Okay, so here this is a cubic meter. You can call it meter per cube. Okay, this one you can call it feet per cube. If I put my little 3 right there, you can get rid of this cu. Okay, this is just telling you it's to the power 3. Okay, feet to the power 3 per second. So that's the capacity. Yeah. So meaning like the spillway is every second this amount, okay, of water. This is a volume, okay, everything that is to the power 3 is a volume unit. So that amount of volume, okay, go through, yeah. Okay, so when we take a look at the Three Gorges Dam construction facts, so we have like a 27.2 million, all right, cubic meter, again, that's a meter plus meter per cube, which is meter to the power 3, okay, and that's the equivalent in cubic yard. Okay, I'm not going to read that for you, all of this. So that's the amount of the concrete that we're using. Okay, then we use 510,000 tons of steel. So we use concrete, we use steel, okay, and then we get rid of about 102.6 million, all right, cubic meter of your ground, which is your earth, to build this structure. So I'm just telling you that it's really big, yeah, and already told you, made of concrete and steel. It's about, this is already told you, to 2,335 meter, okay? That's the equivalent in feet. The top, we already mentioned that in your previous slide. Here it's just emphasizing it is above the sea level, all right? This much. So this is your cross-section cartoon, okay? So cross-section is showing you like what's going on inside of this dam structure, okay? So when you take a look at it very closely, you're gonna see, okay, intake right there, yeah. So this is your reservoir, so that's where your water is stored. It's gonna come in from the river, and the river is always at the low, okay, height, and you're gonna elevate, okay, that meaning like raising that height all the way to here, yeah. So pushing the water that way, and here is your powerhouse and generator right there, okay. And so every time we generate it, what we do is we're going to put this, all right, water, okay, all the way down, and then flow this way, okay, flow this way, and you'll be generating that, right? You see that? So it's got to be staying at an elevated height, so your water surface right here is higher than the surface, okay, of the water in the river, yeah. So we're using this gravity to go down this way, and don't Okay, don't get confused, all right, with how the direction is flowing. So I'm just going to go ahead and show you it is going this way. Yeah. So as the water flow from a height, it is going to generate the kinetic energy, movement, mechanical energy by moving this turbine. Turbine mechanical energy is going to run, all right, run the generator. In the generator, it's going to convert the mechanical energy into electricity. Okay, of course, generator has its own design. Okay, to use this mechanical energy, and then we're going to agitate the electron, okay, so we can be able to understand it, but we're not going to get into details for now for generator, okay. You just think about KE and the NE and the ME to electricity, and then we're going to use a cable, yeah, and I'll branch them up and go to our customers, yeah, consumers. So those are the long distance of power lines right there. All right, application. So we have three common types of turbine. So the very first one is A. Okay, that's your impulse turbine. Pelton wheel. Look at this. Yeah. That's for just low values of turbine. Okay, specific speed. So pretty simple design. Yeah, you can see that how the water is going this way. Here is your inlet. Okay, water is going to come in, and the turbine is going to roll, and then going to generate. Yeah, power. So second one is your Francis turbine, which is B right here. See the structure, okay? Very different structure from A and B. And that's for the moderate, okay, specific speed. So this three, all right, applications, they categorize it by using the speed of the turbine, yeah? And the last one is your Kaplan turbine, and they have a very high, okay, specific speed. So low, okay, moderate, and then high, yeah? Well, just pay attention to the structures. Pretty simple. Okay, and here is bigger one. Yeah. Okay, so what's good about hydropower? So relatively constant supply of water. Okay, we get constant supply. Um, we can control the flood. Okay, we can provide recreation for people. Um, it is not expensive to maintain. It also produces inexpensive power. Okay, we get the power by using free water. Um, and there's no emission. Yeah, and definitely hydropower is in a category of renewable and clean energy, right, source, and you can shut down instantly if you want to. Okay, so these are all good things about hydropower. Right, the downside. So the downside, they definitely require flooding an entire valley or scenic area. Okay, that's not very good. Nobody wants flooding. Even if we want water in the reservoir, we don't want flooding. Okay, so and then mean like the water, some form of water got okay flow into the reservoir. So without the water, there's no business. All right, with the hydropower. So disrupt the natural seasonal changes in the river, and also ecosystems. Okay, can be destroyed. Because you gotta build this thing anyway, and then artificially design. Okay, to get this route. So ends of flooding that helps clean out, all right, the silt in the river. That's also not good for the river. Okay, bigger river. Okay, definitely, well, naturally, river and flooding is kind of like a river recycling of water. Okay, but we are by building the dam, we are disturbing, all right, that process. Okay. Potential worldwide is definitely limited. Okay, it can only offer 5 to 10%, so it can't go worldwide. It can go very, like localized. Okay. Then they're very expensive to build, and like how much concrete, okay, how much metal, all of that go into it. And then dams also, okay, you need to maintain because they can break, because we are storing, okay, massive amount of water in it. Okay. Okay, so this is just a YouTube, alright, link, and you can visit this link and then finish watching, alright, this a very short video, and then it's going to teach you, alright, what that hydropower is. Okay, I'm not going to run the whole thing for you. You can be able to just watch it, but typically it's showing, okay, everything that we have already covered in the lecture. Okay, so now you can see the cartooned and also simulated. Okay, it's kind of fun. And don't limit yourself with this only link. There are thousands and thousands of YouTube videos and also sites that you can visit if you have time, right? To enhance your knowledge. Okay, I think I'm gonna go ahead and stop right here.